So here we're going to look at 2D resultant force using triangular rule. Let's use this example. We have two forces. F1 is 8 Newton and F2 is, let's see, right here, it's 4 Newton, right? And the both applied at point O here. Then we want to find resultant. We want to find sigma F of those two forces. Again, quick review, force is a vector, so it's going to give us the magnitude. What's the number? And also, it's have to be what? Direction. We have to know where is this force located, what direction it's pointing to. So you have to answer both of them, magnitude and direction, that we can define this resultant force. So that's our quest. In the last video, we talking about using two different methods. First one, parallelogram. Second one is triangular rule. But they are actually similar, isn't it? Because triangular, it's basically half of the parallelogram. So in that situation, I'm gonna just talking about triangular rule. Then how do we find it? Let's quick review and apply for this problem. And remember, for triangular rule, they have to be like a head to tail. So for example, I have a force here and I have another force here. If we apply them like a head to tail together, then we will find our resultant. That's our triangular rule. So because you create a triangle. However, those two forces you are saying right now, they are not connected head to tail like this. So how do we do that? Very simple, right? We just move from the head here. We're going to draw parallel line and have parallel line to this F1. And this is, this is F1, so this is F2. Parallel to F2, so we basically move this line to up here. And have to be the same length, because the length dictate the magnitude. The longer the length, the stronger the force is. So this is going to be, I'm label this F1 is 8 Newton here. And this is going to be our F2 now. It's 4 Newton. So how now they are arranged in the head to tail fashion. Now I'm going to use black line here, indicate my resultant. Resultant will be just that. That's our resultant. Okay, so we can solve it. How do we solve it? We have to give you another known. So this problem, not only said 4 Newton and 8 Newton, they also give us the angle between those two forces. They said it's 30 Newton. Okay, well, how do we solve this R? If I move this R here, this R is this black line here. What is this R? What's the length of it and what's the direction? Well, is the direction exactly half of 30 degree 15? Is this angle 15? I'm gonna tell you, it's not. It's not, but that's a common mistake. People thinking those two angles right here, they are the same, but they are not the same. You have to find it in a scientific way, right? But how do we find it? So thinking about it, if I were to draw a parallelogram, I'm going to draw another line here. So we create a parallelogram. Parallelogram, the characteristic for that is, for example, a parallelogram. If this angle is 30, would this angle to be 30? And how about this angle, this obtuse? That's going to be 150. Because 150 plus 30 equal to 180. That is always true for the parallelogram. So this angle will be 152 degree. So knowing that, if that angle is 130, and can you tell me what's this angle gonna be? That's right, 150 degree. Well, then I think we can solve the problem. To make it less messy, I'm going to redraw this really quick. This is an O, and this is a force F1, 8 Newton, and this is our F2 moved up here. 154 Newton, indicated by this side of triangle. And here, the red line here, it's our resultant we're solving. And we do not know this angle, but we do know what? Because this is not half of the 30 degree. I'm going to emphasize that. However, we do know what? This is 150 degree. Because what we just did is we are trying to looking at the top of this triangle. That's where we are now. We are looking at this triangle. Okay, so how do we solve that? We're going to use our trigonometry knowledge you learned before. So this triangle, you know two sides and you know the angle between them. Which law? To find the third side. Right, Cosine Law. So let's review what's Cosine Law. Cosine Law is going to be, if I have an arbitrary triangle here, and this is going to be angle A, B, C, and big letter indicate the vertex and the angle, and also I'm going to use small letter. Opposite to angle A, we have side A. Opposite to B, angle B is B, and C. So ABC is a side length. Cosine law, C squared is equal to A squared plus B squared minus 2AB cosine angle what? C. This is angle C. And then you can do the other ones. And I'm just going to write one more. A squared is going to be B squared plus C squared minus 2BC cosine angle A. Then you can write down the last one, right? You already know the pattern. B squared is equal to A squared plus C squared minus 2AC cosine angle B. Alright, so using that knowledge, we're going to solve R here. Because R squared for this triangle we are solving now is going to be 8 squared plus 4 squared minus 2 times 8 times 4. Then times the angle between them will be cosine 150 degree. Alright, so then pause for a second on your own and trying to put this in your calculator and see what you got. So I'm putting my calculator. So I got R squared equals to 135.43. Then it's R squared, so we're going to try to do a square root of that. Then I have an answer as 11.64, rounding up to the hundredths decimal. And that's going to have a unit of Newton, because that's telling me how long this length is, basically the magnitude of this force. So I bracket up, because that's your answer. The magnitude of this resultant force is 11.64 Newton, right? And you can verify it because this force is 8 Newton, this force is 8 Newton, and this 11.64 looks right proportionally. Then that's like you can use that picture to help you verify if it's at a ballpark, if your answer is right. Okay, then go back here. So force is a vector, resultant force. Two things. Magnitude, you took care of it, 11.64 Newton. But how about direction? That's where we're going now. The direction of this force, how is that related to x-axis? X-axis is always, by convention defined as, horizontal line to the right, right? And that's how we define our direction. It's the convention. For example, that's going to be our x-axis, positive x-axis to the right. And the direction is going to be if this is going to be resultant force, R. So direction is defined from x-axis counterclockwise right? It's counterclockwise from x-axis to the force, to the resultant force. And what's the degree? And that's going to be the direction. What's the theta here? What's this angle theta? If you can find the angle, then you know the direction. So that's where we're going. So in that situation, translate to this particular problem you're working on. This is going to be your x-axis, counterclockwise from here, x-axis to the force resultant. That's going to be our angle theta. If we can find that angle, we know the direction. Well, how do we find that angle? Again, here, don't take a guess for this one because it's not going to be 15 degrees here. You know, you have to using scientific method really trying to figure out the answer. But how do we do that? Right? How are we going to figure out this particular angle? So in order to find that direction, based on all the information given, we cannot solve it yet. Why? Because I'm giving you another known. Because we give like 4 Newton and 8 Newton, the angle between them. But 4 Newton and 8 Newton, we don't know its direction, so we have to define it. So that's what's missing. Now, for example, here, I give you the complete information. We said that this F1 here, F2 right here is going to be relative to x direction. We said this angle is 10 degrees. Okay, so if that's a situation, then you know this F2 is going to be 10 degrees counterclockwise from x direction, and you will know F1 is going to be 10 plus 30, right? 40 degrees counterclockwise from x-axis. Okay, so now we can solve the direction for this resultant. How do we do so? Now let's go back to this triangle right here again. Let's go back to this one. Can we, since you know, we need to find this angle right here, set up. And then look at this yellow highlight triangle. Can you find out the angle, for example, for this one, this angle right here? Okay, and why do we want to find this angle? I will show you in a minute, but can we find this angle? Let's see this angle, we call it alpha. Can we find the alpha? So let's think about it. You have 4 Newton, and the angle between them is 150 degrees. And don't forget, you actually also solve R. R here is 11.64 Newton. So you know 3 sides of this triangle, and you know one angle, 150. Can you find the other angle? Yes? So if I were going to make this a little bit, isolate this triangle out, so you know this is 8 Newton, this is 4 Newton. The angle between them is 150 degrees, and this side, it's resultant, 11.64, we just calculated. And our goal right now is finding this angle alpha. How do we solve it? Trigonometry, right? Sine law. So that's where we're going. So earlier you used cosine law, now it's a sine law. Sine law, let's quickly review. If in this triangle right here, how do we write down sine law? A, the length, over sine A is going to be equal to B over sine B of that angle, C over sine sine C. So knowing that, we are going to apply for this problem. 8, that's the side, over the angle opposite to this side is going to be your sine alpha. And we can use 4, but if you use 4, you have to know this triangle right here, which we don't. Then, however, don't forget, you have this resultant figured out already, 11.64. And Do we know the opposite angle? Yes, 150, sine 150. So here you have an equation. You have one equation and one unknown. The unknown is your alpha. So can we find this alpha? Yes. So cross multiply 11.64 sine alpha is going to be equal to 8 times sine 150. So now we're going to solve it. So put in your calculator. I hope you're doing that as well. 8 times sine 150 degree. Then we'll divide by 11.64. That's my sine alpha. Sine alpha is 0.3436, right? And here we're going to try to find the angle itself, alpha. So we're going to do inverse sine of this angle. So inverse sine of that angle is going to give us the degree of 20.098 9 something 5. Anyway, so here, and let's just go ahead round it. So it will be 20.1 degree. So alpha is calculated, the angle 20.1 degree, which is this angle right here. Well, how would solving this angle help us finding the direction of our resultant? Because that's our goal. So basically, is this, we're curious, this theta right here, right? So now let's think about it. Now let's go back to this first picture right here. And this angle, we just found out, which is our alpha, and this is alpha, as 20.1 degree. If alpha is known, can you tell me what's going to be the angle here? So here I'm actually going back to the parallelogram here. This will be your alpha as well, because it's a characteristic of parallelogram, right? For example, if I would draw this line right here, would this angle same as this angle? Yes, they do. That's the attribute of the parallelogram. This alpha, this will be alpha. So using this geometry, then you can solve this problem. If we don't use this, we're stuck. So review that. So if that's alpha, this is alpha. Now we also, remember earlier we're missing this information, it's 10 degree. Where is this force F2 is located? We said it's 10 degree from x-axis counterclockwise. Now, how do we define the direction of this magnitude? It's defined as what? From x-axis, counterclockwise rotation. How much is rotated? Remember, this is our resultant, R here. So from x-axis counterclockwise, touching the resultant right here. That's our resultant force. And that's going to be our angle, theta here. That's what we're solving. Now maybe you start to looking at why we need to find this alpha here. Because this alpha, we just calculated. And we also know this 10 degree right here. 10 degree plus your alpha is gonna give you the direction of this resultant. We are almost there. So the direction, theta. Let me write down at the bottom. So this theta, as we have concluded, is going to be equal to the 10 degree plus this alpha. That's 10 plus 20.1. That's going to be 30.1 degree. So we got the theta as 30.1 degree. It's going to be right here. So that defines the direction of this resultant force. Again, the direction of any force is defined by this convention from x-axis counterclockwise, how much degree? And that's exactly what we did, 30.1 degree. For this situation is 10 degree plus this alpha. All right, so that's for this problem. And this is the first example for 2D resultant. and we find out both magnitude and the direction. All right, I'll see you next time. Bye.